Kia ora and welcome to this video on question 2 of the 2022 Scholl Calc exam. This question's got 3 parts to it. The first is a discriminant problem, fairly reasonable question. Then part B and C involve triangles. Part B is going to make use of the sine rule and some identities, and part C is going to make use of the cosine rule and some differentiation. Okay, part A. Consider the equation, a quadratic equation. For what values of k will the equation have 2 distinct real roots? Okay, so distinct means different, and then with the same sign, so either they're both positive or they're both negative. There's 2 criteria that we need to consider. First up, let's get the quadratic into standard format. Rearranging it, so we've got 1 minus k all times x squared. We've got minus 4 lots of, no, not 4 lots of, minus 4, and also minus 2k all times x. Notice I've got the minus on the outside of the brackets there. And then we've got 10 minus k is the constant term, equals 0. The quadratic's now in standard form. 2 distinct roots means that the discriminant is greater than 0. So if we go with the discriminant there, b squared minus 4ac is this dude squared minus 4 lots of 1 minus k times 10 minus k, and that's greater than 0. Got to be real careful here with expanding. The minus squared does nothing, but expanding 4 plus 2k, we've got 16 plus 16k plus 4k squared. Take away 4 lots of 10 minus 11k plus k squared. The k squared terms cancel, and we've got 16 minus 40 is negative 24. And 16k plus 44k is 60k. So k is greater than 24 over 60, which is equal to 0.4. Now remember that k is the coefficient in front of the right-hand side parabola, so it refers to its steepness. So if k is large, then the parabola is steep, and we ensure that there are 2 solutions. Now, we also want the solutions to be both the same sign. So if I look back at this polynomial, it's in standard format. If I divide everything through by 1 minus k, sometimes referred to as a monic polynomial, I don't need brackets there anymore. Think about what this would look like if it factored. If it factored, it would be something like x minus alpha and x minus beta, where alpha and beta are the roots. And if we want alpha and beta to be the same sign, then this constant term here, which is the product of the roots, is minus alpha times minus beta. For alpha beta to be the same sign, for alpha and beta to be the same sign, when alpha beta will be greater than 0. When we multiply the roots together, we get a positive quantity. So we need to just solve 10 minus k greater than 1 minus k. So 10 minus k over 1 minus k is greater than 0. Think about a number line. There's 2 values of k here where this thing changes its behavior. K equals 1 and k equals 10. when k is equal to 1, the thing's undefined, and that's because if we go back to the original problem, if k is equal to 1, it's no longer a quadratic equation. The x squared terms would cancel both sides. We'd have a linear equation with only one solution, and the question's saying it has two distinct solutions. So k equals 1 is not a possibility. And then k equals 10. K equals 10 makes this fraction equal to 0. If we go back and we make k is equal to 10 in the problem, so if we make this 10, you'll find out that there are two solutions, but we've got x squared minus 4x equals to 10x squared plus 20x, and the 10's cancel on either side. This is a quadratic that's got x equals 0 as a solution, and technically 0, well, what is the sine of 0? So that's also, it's not positive or negative, so that's also a value k that doesn't work. Testing in between these points, if k is between 1 and 10, then the numerator of this fraction is positive, and the denominator is negative, so we don't want that. So that's bad. Turns out that if k is bigger than 10, the numerator and denominator are negative, so positive overall, and then also in here it works. But remember, we wanted k to be bigger than 0.4. That was already a restriction we had. So the final answer is k is between 0.4 and 1, or k is bigger than 10. Alrighty, part B. Consider the triangle ABC shown. Now this is not drawn to scale. It should say that, but it's not to scale. The exclamation mark. And I'm going to explain why in a sec. But we've got AB is 16, AC is 12, and the angles alpha and 2 alpha. Find the area of the triangle. So the area of a triangle is either half base times height, or a half AB sine C. And because we've got two sides here, I'm going to call this one A and this one B. We just need this angle up here, which I'm referring to as C. Sorry, apologies for the changing lettering there, but half AB sine C. So that's where we could start. Area equals a half times 16 times 12 times sine of pi minus 3 alpha. Okay, pi is 180 degrees, which means that this angle up here is 180 degrees minus 3 alpha. So if we tidy this up a little bit, we've got 96 sine of pi minus 3 alpha. If you make a graph of it, making sure that you're in radians, you'll find that the pi minus is a shift in a reflection. If you graph it, you'll see that it's just sine of 3x, sorry, sine of 3 alpha. If you didn't spot that this simplifies to that, you can use the compound angle formula, which would be sine of A minus B is equal to sine A cos B minus cos A sine B. So I would go sine of pi minus 3 alpha is sine of pi cos of 3 alpha minus cos of pi sine of 3 alpha. Sine of pi is 0, so that term disappears. Cos of pi is negative 1, so that term becomes negative 1 sine 3 alpha. Okay, so that's a simplification. That's quite useful to us. Going back to the problem, we've got to somehow find out the angle alpha, or at least understand the size of alpha. And that's where we can use the sine rule. The sine rule says that any side A divided by the sine of the angle opposite is equal to any other side B over the sine of the angle opposite. So for this one, I can go 12 over sine alpha is equal to 16 over sine of 2 alpha. That's true for any triangle. Okay, so we're going to use that information to understand what alpha is. Cross multiplying this, 12 sine 2 alpha is 16 sine alpha. Sine 2 alpha using the double angle formula is 2 sine alpha cos alpha. And we've got a sine alpha on both sides there, which we can cancel because we know it's not 0. Alpha is not equal to 0, and alpha is not equal to pi. That would be that triangle wouldn't exist. So we cancel out that, and we've got cos alpha is equal to 16 over 24, or 2/3. At this stage, I reach for the calculator and I go, well, what is alpha? If I take the cosine inverse of it, and we can do this because the cosine graph looks like this, and we know alpha is somewhere between 0 and 180. 2/3 comes through here, so that's the solution we want. Clearly not that solution, it doesn't make sense, but this one here, yep. So if I take the cosine inverse of 2/3, I'm just going to turn it into degrees so I can interpret it. Turns out to be 48.19 degrees. If I then take this angle and chuck it up into here, I'm going to get the area as a decimal. And I don't want that. The question did say find the exact area. But 48.19 degrees poses an interesting problem, because if I go back to the diagram, if alpha is 48.19, then 2 alpha is 96.38. The diagram is definitely not drawn to scale. I got GeoGebra to do a diagram to scale. I used circles to make sure that the sides had the right length. And you can see it's an obtuse triangle. There's actually 2 possibilities, because you can see that there's 2 intercepts there. This length is also 12. And I must say, when I first looked at this problem, I thought, and you might have thought the same thing, just chop this triangle down here, make it a right angle. We know that cos alpha is equal to 2/3, so we can find this side and this side. Eventually we can find that side, and then we've got half base times height. But you get the wrong answer because in this case the base is too wide. Looking at our diagram, it's a bit more complicated. So we still need to find 96 sine 3 alpha, but what we're going to do instead of using Pythagoras and splitting triangles in half is we're going to write sine 3 alpha is 2 alpha plus alpha. Use the compound angle formula. And then the double angle formula. Okay, the sine 2 alpha bit there. Sine 2 alpha is 2 sine alpha cos alpha. And then the cos 2 alpha one, 1 minus 2 sine squared alpha. So that's cos 2 alpha, there's that one. And then we're almost finished. Remember that cos alpha was equal to 2/3. That's equivalent to having a triangle, alpha there, adjacent side 2, and hypotenuse 3. It doesn't have to be in 2 and 3, it could be 4 and 6, it could be 20 and 30, but it's that ratio, which means that the sine of alpha can be found. This side here is root 5. Sine of alpha is equal to root 5 over 3. And then we can plug this information, cos alpha is 2/3, sine alpha is root 5 over 3, into our expression. Therefore, the area is equal to 96. This is a bit messy with surds, but we've got 2 times sine alpha times cos alpha squared, so 4 over 9. And then we've got plus 1 minus 2 sine squared alpha, so 1 minus 2 lots of sine alpha all squared, so 5 over 9, 10 over 9, times sine alpha. Okay, there's a common factor of root 5 over 3 there, so I'll pull that out the front. And then we've got 8 over 9 minus 1 over 9 which equals 224 root 5 over 9. Okay. Part C. Consider a different triangle which has side lengths that form a geometric sequence with a common ratio of r. So a geometric sequence would be something like a, ar, ar squared, where the multiplier is the ratio. It's like an exponential pattern. For simplicity though, I'm just going to, instead of that, I'm going to say the middle term is 1, this is 1 over r, and this is r. Okay, it just makes it a little bit easier to work with in the maths. So we've got a triangle. Middle side is 1. The longest side, if we, without loss of generality, assume that r is bigger than 1, then this will be r, that's the biggest side, and 1 over r, a smaller side. If alpha is the angle opposite the side that's neither shortest nor longest, so alpha. We've got one angle and 3 sides, so the cosine rule applies. C squared is equal to a squared plus b squared minus 2ab cos c. So plugging in our information, we've got 1 squared equals r squared plus 1 over r squared minus 2 times r times 1 over r cos alpha. Okay, that's our equation that we're going to, or that's our equation that links alpha and r together. If I make cos alpha the subject of this equation, I get that. And the question's asking us to find the maximum value of alpha. If we think about the cosine graph, I've already drawn it before, but let's redraw it. Alpha, as alpha increases, the cosine alpha decreases. So the biggest value of alpha will be the minimum value of cosine alpha. So if I just let cosine alpha equal to y, and then find dy dr, I'm going to make this equal to 0 to find the minimum. So we've got dy dr, the half does nothing, differentiate the r squared, differentiate the 1 over r squared, 1 over r squared is r to the minus 2, so it differentiates to minus 2 over r cubed, and then the minus 1 disappears, equals 0. So 2r must equal 2 over r cubed, or r to the 4 must equal 1. R is not negative, it relates to side lengths of a triangle, so r is equal to 1. That generates the optimum value of cosine alpha, which is also the maximum value of alpha. So therefore, r is equal to 1 tells us we have an equilateral triangle. And therefore, alpha equals 60 degrees is the max. Now, the question did say that the three sides, it implied that one of the sides was shorter and one was longer. So if alpha equals 60 degrees is not possible, because that would generate an equilateral triangle, if r is equal to 1 as well, then I guess you could make the angle 59.99999 degrees. If I just show you a picture of this I've made, what I've got there is the 1r and r squared triangle, and if I slide r back to 1, there's my equilateral triangle with an angle of 60 degrees. If I make r bigger, the angle starts decreasing. That's quite buzzy. But as we change our triangle, the angle keeps decreasing, starting off at the maximum of 60 degrees. So hopefully that helps you understand what's going on there. Catch you in the next video.